So welcome you all. Today I am going to deliver my lecture 2 of module 3, which is on gas transfer and air stripping process. So if you remember, in the previous lectures we have seen the concept behind this gas transfer and the air stripping process. Then we learnt about the mass balance analysis, Henry's laws. So today what we are going to cover in this lecture is dynamic approach for design of stripping column, design equations which are used, then stripping factor, mass transfer coefficients, and then based on that we will have certain numericals to illustrate the design concept of stripping tower. So if we see this again similar to our equilibrium analysis, here we will be learning about the dynamics analysis of stripping column. So this basically considers like counter current flow system. So in this system what happens, this wastewater enters from the top and comes out from the bottom, whereas the air is inserted from the bottom of the tower and it comes out from the top of the column. So it's like a counter current system. So in this system, if we consider the flow rate of liquid like L, which is the flow rate of the wastewater here, and then G, which is the flow rate of the air we insert for stripping of the dissolved gases, VOCs or ammonia, nitrogen from the wastewater. So if this G is the flow rate of that air and C is the concentration of solute in the water, and P is basically the concentration of solute in the air, and this R, if you see, that is the universal gas constant. And if we consider this is the column where this is the packing media, and in this packing media let's consider this ZT, basically that is the height of the stripping column. So in this, if we consider the cross sectional area like this, cross sectional area of this column, this is like AX. So for this dynamic equilibrium of a column, what are the various design equations we use for determination of the height of the column, for determination of the height of the packing media, cross sectional area. So many more dynamic parameters we can analyze using this dynamic analysis. Then if we see various design equations, so first of all we need to find out the height of the stripping tower, which is equal to Z. Z is equal to HTU into NTU. STU, basically this is the height of the transfer unit, where NTU, that is the number of the transfer units. So in a given column we can have number of stages, so accordingly the number of transfer units will increase, and accordingly then we have to design the appropriate height of the column. And in this, if we see that height of the transfer unit, basically it depends upon the flow rate of the wastewater, the mass transfer characteristics of the solute, and also to the cross sectional area of the packing medium. So this we can find out using this equation, where STU is equal to L, which is the liquid flow rate or the wastewater flow rate in this case, and KLA is the mass transfer coefficient, and A is basically representing the cross sectional area of the stripping tower. So similarly in this equation, if we see this KLA we have to find out, which is basically the mass transfer coefficient, which depends upon the characteristic of the solute and the characteristic of the wastewater and the concentration gradient between the water and the air. So how to determine this mass transfer coefficient? For that we can use this equation, which is basically the ROC, which is equal to minus KLA VOC. This is mainly referred to for VOC removal, into C minus CS, where C is basically the concentration of the VOC in the water or the wastewater, and then CS basically it's saturation concentration, where R VOC represents basically the mass transfer rate of VOC. So this is the equation which we can use to determine the KLA value, which is used in the previous equation to determine the height of transfer unit. So this KLA, basically determination of KLA VOC, that is little bit difficult. So for this determination we use this equation, which is intercorrelated with the diffusion coefficient of oxygen and VOC. So here this equation we use, the KLaO2 we can determine, and this by using this diffusion coefficient of VOC and oxygen we can find out the mass transfer coefficient of VOC, which is to be used in the design equation to determine the height of the transfer unit. And then if we see in this equation, this n value, which is basically a coefficient which depends upon the type of the aeration, the method of the aeration, and the characteristic of the solute, the packing media, the type of the towers we are using. So this you can see the value of n, which is equal to 0.5 for packed column and having mechanical aeration system, with the power intensity of the equipment used, which is less than 100 watt per meter cube. And in case of basically diffused aeration system in a packed column, the value of n that must be taken equal to 1 for the power intensity less than 100 watt per meter cube. So then we have to find out the number of the transfer unit which is required, NTU, which is equal to C0 minus CE divided by CO minus CE minus C dash O, which is basically the equilibrium concentration, whereas C0, that is the initial concentration of solute in the water, and CE is the final concentration of the solute in the water or the wastewater. So using this equation we can find out number of the transfer unit required for this stripping column. Then finally we can find out the total height of the column required. And for this, in the previous equation, if we see this C dash 0, which is the equilibrium concentration, this can be find out by using this equation, which is the C dash 0, which is basically the equilibrium concentration, is equal to L by Z into PT divided by H into CO minus C, where this L is the flow rate of the water, G is basically the flow rate of the air, PT is the partial pressure of the solute, and then H is basically the Henry's law constant, and CO and CE basically they are the initial and final concentration of solute in the water. So by using this equation we can find out the value of this equilibrium concentration. If we see this L by Z and into PT divided by H, inverse of this entire term, that if we take equal to S, which is equal to G by L into H by PT. So if we take inverse of this equal to the stripping factor, then this equation can be converted in this form, where this C dash 0 that will be equal to C0 minus C divided by S, and this is the simple equation which we can use for determination of equilibrium concentration in terms of stripping efficiency. So now if we substitute this value of equilibrium concentration, that is C dash 0, in the previous equation for NTU, so this will be the final equation, which is equal to NTU equal to S divided by S minus 1 log of C0 divided by CE S minus 1 plus 1 divided by S. This is basically the final equation we can use for determination of the number of tons per unit required for an ammonia strippers or an air stripping column. In this equation, if we see if S is equal to 1, it means that this represents the minimum amount of the air required for stripping process, and that becomes very economical. But if we take S is more than 1 to ensure complete stripping of the solute from the wastewater, in case S is less than 1, it means there is insufficient air is used, and this will result into lower stripping efficiency of the column. So normally this stripping factor, the value of S varies from 1.5 to 5. So depending upon the economy of the process, we can use a factor of 2 to 3 as per the design. So this, if we see, this is a table which contains the design values for different design parameters. If we see, that is the liquid loading rate. So for VOC removal and for ammonia removal separately in these two columns, these design parameters which are used for design of stripping tower. So like if we see the first parameter like liquid loading rate, so for VOC removal the value is 600 to 1800, whereas for this ammonia removal the value is very less, that is 40 to 80 liter per meter square per minute. So this is basically the for VOC removal, and this column will give the values for the ammonia removal. Similarly, G by L ratio, that should be 20 to 60 in case of VOC removal, while in case of this ammonia removal a huge amount of air is required. So this basically affects the economy of the process. And similarly, this is the stripping factor, which is, this is the symbol S, and because this is a unitless, and so here for VOC this may be taken from 1.5 to 5, and similar values we can take for ammonia removal. So this table gives all different parameters like the type of the packing media we use, like pall rings or maybe saddles or etching rings, whatever we use, this the packing depth, factor of safety, wastewater pH. Like if we see pH for VOC removal, this is 5.5 to 8.5, whereas in case of ammonia removal this is very high, it should be 10.5 to 11, more than 11. So it has more efficient stripping at this pH. So basically this table describes the typical design parameters which are used for design of stripping column for removal of VOCs as well as for removal of ammonia, which is normally used in the industry. These towers for removal of ammonical nitrogen. Similarly, there are aeration systems which are used for removal of VOCs. So now let us see about the advantages and disadvantages of packed tower strippers. We can see it's very effective for volatile and even semi-volatile organic compounds. So for VOCs removal it is very effective, but if we see like in terms of ammonical nitrogen removal, the stripping efficiency is comparatively less than this VOC, because in case of VOC removal it can remove more than 99% of the VOCs, but ammonia strippers normally they results into 70 to 80% of maximum stripping efficiency. So this is also an economical way of removal of VOCs and ammonical nitrogen compared to the other treatment systems. And if we see for VOC removal, it implies very low G by L ratio, whereas in case of this ammonical nitrogen, this is very high. So, and it ensures complete removal of VOC. Okay, so also it can be used for wide range of applications having extended air flow rates. So these are basically the advantages of the packed bed tower air strippers. But if we see the disadvantages, so that is not good for the contaminants which are not readily strippable, like having the Henry constant less than zero point 0.1. So this type of compounds they cannot be stripped off, and it might be costlier since it requires a high towers and number of pumps, number of blowers, along with number of piping works, so it becomes a little bit costlier. And then there is a one more practical problem associated with this, that is the fouling of the packing media. And the another disadvantage, like we are transferring the pollutant from water to air, so air gets contaminated, which is one of the major disadvantage of this process and requires high maintenance cost. So these are the advantages and disadvantages of the air stripping towers used. So now let us we see certain numericals which are based on these concepts. So let us see first numerical. Determine the theoretical amount of air required at a temperature of 20 degrees centigrade to reduce the ammonia concentration. So here the solute concentration, that is ammonia, which is 40 milligram to 1 milligram. So we have to reduce out the ammonia concentration from 40 milligram to 1 milligram in a treated wastewater having a flow rate. So flow rate is this much, 4000 meter cube per day, and the pH of the wastewater has been increased to a value of 11, that is basically required for in case of ammonia stripping process. The Henry's law constant for ammonia at 20 degrees centigrade, that is given, like value of H is given 0.75 atm. And also if we see that the air entering at the bottom of tower does not contain any ammonia, so initial concentration of solute in the stripping media like air what we use in this case, so that is 0. So here first of all what to determine, that is to determine the amount of air required. So basically that is G by L ratio we have to find out. And for this, first of all, we have to find out the molar fraction of the solute present in the water and the air phase. So here if we see that the molar fraction of the solute that is present, ammonia, in wastewater, that is will be equal to number of moles of gas divided by number of moles of that gas plus the number of moles of water. So it will give molar fraction of that ammonia which is present in the form of gas into the water or the wastewater. So here if we see that the concentration of ammonia that is given as 40 milligram per liter, so 40 into 10 raised to the power minus 3 divided by 17. So this will give the number of moles, because 17 is the molecular weight of the ammonia. So here we can get the number of moles of that gas divided by the number of moles of gas. So again the number of moles of gas here, 40 into 10 raised to the power minus 3 divided by 17, that is equal to 4.24 into 10 raised to the power minus 5 moles of ammonia per mole of H2O. Similarly, if we see that is C, which is the molar fraction of ammonia that is present in the effluent. So similar way, that is 1 milligram per liter. So 1 milligram into, convert it into gram divided by 17, which is the molar weight of the ammonia. So divide it by this, so you will get number of moles, and this 55.5 is the number of moles of water which is present in 1 liter. So that is basically that is 55.5 plus this is the number of moles of ammonia. So total number of moles of water plus ammonia. So now if we calculate, the value of C comes equal to 1.06 into 10 raised to the power minus 6 moles of ammonia per mole of H2O. Then similarly we can find out the molar fraction of ammonia in the treated effluent, which is equal to Y and can be given by this equation. Y is equal to H divided by Pt into C0, where H is the Henry's law constant, which is given equal to 0.75 atm, whereas this Pt is the 1 atmospheric pressure. So this here we can put 1 atmospheric pressure, and then this C0, which is molar concentration of ammonia gas in the wastewater initially present, which is equal to 4.24 as we have worked out earlier. By putting this value in this equation, we get the value of the effluent molar concentration of ammonia, which is equal to 3.18 into 10 raised to the power minus 5 number of moles of ammonia per mole of air. So now if we see, because we need to determine G by L ratio, which is equal to Pt into H into CO minus Ce divided by Ce. So this, if we write equal to CO minus Ce divided by Y, because this if we replace as per this equation, so we will get the final equation equal to this CO minus Ce divided by Ye. And in this again, if we see this C is very less than CO, so here we can use this CO minus Ce equal to CO, and then this G by L ratio, that will be equal to CO divided by Ye. So CO value already we have got here, that is 4.14 into 10 raised to the power minus 5, whereas this value of Ye, which is equal to 3.18 into 10 raised to the power minus 5, we can substitute here, and then we can find out the ratio of G by L, which is equal to 1.3 moles of air per mole of water. So this is in terms of moles, but now we have to determine how much meter cube per meter cube of water it will be required, or per unit volume of flow it is required. So we have to convert this moles into their weight and volumetrical unit. So here if we see at 20 degrees centigrade, like per mole of air has a volume of 24.1 liters. So if we have 1.3 moles, so this much liter of this air will be required. And for water, if we see 1 mole of water will have 18 gram of weight. So if we multiply with 18 its molecular weight and divide by 1000, which is to convert into liter, which is the density of the wastewater, 1000 gram per liter. So this is basically coming equal to 0.018, and thus G by L ratio in terms of this, if we put this value 31.33 here, and this the volume of the water equal to 0.018, so this will be 1741 liter per liter, or we can say it's the ratio of the same unit, so we can say like 1741 meter cube per meter cube of wastewater. From this G by L ratio we can find out how much air is required for a given rate of flow. So the rate of flow we have 4000 meter cube per day. So if we multiply with this G by L ratio, which is 1741 meter cube per meter cube, and convert this day into minutes, so one day having 1400 minutes, so if we convert, so it will come 4835 meter cube per minute. So this is basically the amount of air which will be required per unit time, which is per minute. So now let us have some example on the determination of height of the stripping column. G by L ratio we have already seen in the previous examples. So now let us learn how to find out the height of the stripping tower, which is required to treat the wastewater. So we can assume this data, like flow is given like 4000 meter cube as per the previous example, and the diameter of the tower we can assume 4.13 meter, and there is packing media which is made of 25 pal rings, and then ammonia concentration again if we see that is same 40 to 1 milligram per liter, this must be reduced. Henry's law constant already we have seen, this is 0.75 atm at 20 degrees centigrade, and here also we have assumed this air does not contain any amount of initial ammonia, and KLA value is given, that is 0.0125 per second. So using this values, how we can find out the height of the stripping column. So let's discuss how to do this. So if we see, first of all we have to assume the packing factor. So for packing factor we have to see the size of the pal rings, which is 25 So from that table which I have earlier shown to you, so that is this table if we see, so pal rings for 25 size, the packing factor which is 30 to 60 for this VOC removal, and this for ammonia removal this is 30 to 60. So here in between 30 to 60 we can assume any value. So here we have assumed that is 50. So similarly the stripping factor, this is 1.5 to 5. So that is given in the table. So here we have assumed that is 3. And similarly we can assume a pressure drop of 200 Newton per meter square per meter. So accordingly we have to see the equation which is used for determination of the height of the transfer unit. So this is basically S2U is equal to L divided by KLA into cross sectional area of the column. So here this liquid flow rate which is given as 4000 meter cube per day, if we substitute the value, and this day if we convert in terms of seconds, which is 86,400 seconds in a day, and then here this KLA value that is given as 0.0125 per second. So this is the value we have substituted. Similarly this is cross sectional area, so which is the diameter is given 4.13 meters, so pi by 4 d square, this diameter is 4.13, so square of this will give you the value of this S2U. So by calculating this, the STU value which is the height of transfer unit, that comes equal to 0.028, and then similarly we can find out the number of transfer unit, which we can use this equation, which is S divided by S minus 1 log of CO divided by CE into S minus 1 plus 1 divided by S. And here if we see this value of stripping factor, we have assumed equal to 3. So if we put the value 3 divided by 3 minus 1, and similarly this CO which is in milligram per liter, so 40 milligram per liter, and then this is 3 minus 1, this is S minus 1, and this again S, that is equal to 3. So substituting this value, what we will get, that is number of the transfer unit which is required, that is 4.94. So then we can find out this height of the transfer unit into NTU, that will equal to the total height of the column required for the packing media, and which if we see STU value we have got 0.28, and similarly NTU from the equations we have got 4.94. If we multiply we get a value of 1.38 meter, so which is the required height of the packing media in the column. So this we can take approximately equal to 1.4 meter. So this is how we can also work out the height of the column as per the dynamic analysis of the stripping column. And then similarly one more example we can take, which is on the determination of mass transfer coefficients and Henry's constant. So here if we see the example, so determine the mass transfer coefficient and unitless Henry's constant of the benzene that can be stripped in a completely mixed activated sludge reactor equipped with diffuse aeration system. So here the aeration system is defined, the completely mixed activated sludge reactors are defined, and we have given this following data to find out the mass transfer coefficient and Henry's law constant. So this air flow rate, which is given 50 meter cube per minute at the standard temperature conditions, oxygen mass transfer rate is given 6.2 per hour. Then the influent concentration of the benzene, which is given 100 microgram per meter cube. Similarly, this Henry's constant, that is given as 5.49 into 10 raised to the power minus 3. The unit, if we see, that is meter cube dot atm per mole. And here if we see that n value, which is the coefficient of the equation, which is equal to 1, temperature is given, that is 20 degrees centigrade, and this diffusion coefficient is also given for oxygen and for benzene also, which is 2.11 into 10 raised to the power minus 3, 10 raised to the power minus 5 centimeter per second. Similarly, for benzene it is very less, which is 0.96 into 10 raised to the power minus 5. So for this data, let us see the equations to find out the mass transfer coefficient of benzene. So here we take KLA VOC, VOC if we presume as benzene. So this will be equal to KLA O2 in bracket, that is the ratio of diffusion coefficient of VOC divided by diffusion coefficient of oxygen. So all these values are given. So we can put these values here. We can find out that is the mass transfer coefficient of benzene, which is 2.82. So this is the answer. And similarly, we have to calculate is unitless Henry's constant, which is equal to H divided by RT. So H value is already given, and this R value is basically this at standard temperature and pressure. So we can assume this R value, and then temperature is like 20 degrees centigrade. So this is 273.15 plus 20. So that will get converted into Kelvin. So by putting this value, we can find out the unitless Henry's constant equal to 0.228. So for this, you can use this Metcalfe eddy, where this stripping process is nicely described. So with this, I conclude my lecture. Thank you.